Welcome to our second lecture on instrumental variables. In this lecture, we'll be talking about the local average treatment effects model. So the idea today is to go beyond the textbook IV model, which assumes homogeneous treatment effects. So that model, if you recall, was y equals alpha plus beta d plus u. And this model implies that everybody has exactly the same treatment effect, beta. But in reality, treatment effects differ across people. In other words, they are heterogeneous. So that's what we'd like to allow for today. The question we're going to ask is what, if anything, does IV tell us if treatment effects are in fact heterogeneous? This is going to give rise to what is called the local average treatment effects model. I will be going through a number of different topics today, some of which I will only be able to cover in outline, some of which I will allude to, and others I'll look at in a bit more detail. But if you'd like to see additional information about these topics, including some more steps in the derivations and some extensions, I'd highly recommend that you check out my lecture notes on treatment effects. You can click the link on these slides. The relevant chapters are 5 through 7. I also have some slides on marginal treatment effects, which you can view by clicking on these two links, Part 1 and Part 2. Those slides are partially covered in the lecture notes, but there's a little bit of extra material on the slides that I haven't yet had time to type out in detail, so you might find those helpful as well. So let's very, very quickly review the case of IV in a homogeneous effects model with a binary treatment and a binary instrument. This gives rise to what is typically called the walled estimand. So you recall that beta IV, the IV population estimand, the thing that we're trying to estimate, is defined as the covariance between z and y divided by the covariance between z and d. Now, if we multiply both the numerator and the denominator by the variance of z, so that's just the same thing as multiplying by 1, we end up with a slightly more complicated looking expression, but it's actually quite helpful. So now the numerator is the covariance of y with z over the variance of z. And we recognize that as the slope from a population regression of y on z. So what will that slope be? Well, a bit of work with paper and pencil will show us that that's actually just the difference of means when the mean of y when z is 1 minus the mean of y when z is 0. And proceeding similarly for the denominator in that fraction, the covariance of d with z divided by the variance of z is just the slope in a population linear regression of d on z. And again, because z is binary, you can work out that the slope from that regression is just the difference of means, the mean of d, the mean of d when z is 1 minus the mean of d when z is 0. And this particular ratio is usually called the walled estimand. Let's take it apart. The numerator is simply the difference of means for y when z is 1 relative to when z is 0. This is often called the intent to treat effect. And the easiest way to think about it is to imagine that this instrument z is actually a randomized offer of treatment in an experiment. So what's the idea here? Well, imagine we're doing a social experiment, and we're going to randomly offer some people maybe the opportunity to participate in a job training program or something like that. We typically can't force people to participate in programs. We can only offer them the opportunity to participate. So the offer, z, which we will assume is randomly assigned for the moment, is not necessarily going to be the same thing as the treatment take-up, which I'll call d. So some people don't want to take the treatment even if you offer it to them. And indeed, sometimes people who aren't offered the treatment may nevertheless find some way to get it. This idea that the treatment offer might not be the same thing as treatment take-up, in other words, the people you randomly assign to treatment and control might not perfectly coincide with those who actually end up getting treated and who actually end up not getting treated, this phenomenon is often called noncompliance. Sometimes it's also referred to as a randomized encouragement design. In this setting, however, z is randomly assigned. So it's a perfectly valid question to ask, what is the causal effect of z on y? That is called the intent to treat effect, and that is precisely what the numerator of the walled estimand tells us in this context. So this is just the average treatment effect of offering somebody treatment. Now, the Wald estimand takes account of the fact that this ITT effect, this intent to treat effect, is in a certain sense diluted by people who are offered the treatment but don't take it up. So let's think about it like this. We have this effect of offering the treatment, but if we think that the mere offer of the treatment, so simply offering you the chance to participate in a job training program, that maybe shouldn't actually affect your employment prospects. It's only participating in the program that should have an effect. Well, in that case, if we think about the ITT, the trouble is that it includes a number of people as quote-unquote treated who really didn't get the treatment. They were treated in the sense that their Z was 1, but maybe they didn't take up. So what the Wald estimand actually does is it looks at two different ATEs. So it looks at, first of all, the ATE of Z on Y. So this is the ITT effect, the average treatment effect of the randomly assigned offer on some outcome. But then it also looks at the causal effect of Z on D. So randomly offering some people the chance to take the treatment presumably has a causal effect on whether they take it or not. So what we're doing is we're taking the ratio of two causal effects. Each of them is a perfectly valid and perfectly meaningful causal effect. They may be of interest. So we're looking at the causal effect of the treatment offer on the outcome, and we're dividing that by the causal effect of the treatment offer on treatment take-up. So in a homogeneous effects model, this ratio is exactly equal to the average treatment effect of D itself. So that's what we'll remember from our lecture on basic IV. But suppose that we're not willing to assume any longer that that treatment effect is the same for everybody. So if different people can have different causal effects, then when does this ratio give us anything meaningful? Does it ever give us something meaningful? That's the question we're going to be looking at today. Let's take a closer look at this ITT effect and try to understand in more detail what I meant when I said that it represents a kind of diluted version of the treatment effect. This is a very famous experiment. It's called Moving to Opportunity, and it basically randomly offered housing vouchers to some families in order to encourage them to move to a more affluent neighborhood. And the question here was whether there might be some neighborhood effects on people's job market prospects and other long-term outcomes. So in this experiment, it turns out that among the people who were offered the voucher to move to a different neighborhood, only 50% of them actually moved. So Z equals 1 means that you were offered the voucher. So only 50% of those families who were offered the voucher actually took advantage of it and moved to opportunity. At the same time, among the families who were not offered a voucher, that would be Z is 0, 20% of them moved nonetheless. Because, of course, you can't stop people from moving neighborhoods, just like you can't force them to move from one neighborhood to another. So let's recall our favorite expression by now for the link between observed and potential outcomes. Y is equal to 1 minus D times Y0 plus D times Y1. And let's also denote by P with the subscript little z the probability that D equals 1 given that Z equals little z. So this PZ tells us the share of people with a particular treatment offer who actually take up treatment. So in particular, P1 would be the share of people who take up treatment among those who are offered, and we know that that's 50%. P0, on the other hand, that's the share of people who take up treatment among those who are not offered. And here, in this moving to opportunity example, we know that that's 20%. So P0 is 0.2. All right, now let's think about the observed mean, the observed conditional mean of y, given that z is 1. Well, if you think about it for a moment, and you look at our expression for y in terms of the potential outcomes y0 and y1, you'll see that this expectation of y, given that z is 1, is actually a mixture of y0 and y1 for some different types of families. So in particular, we're just using iterated expectations here. The expectation of y, given that z is 1, is equal to 1 minus p1 times the expectation of y0, given that z is 1 and d is 0, plus p1 times the expectation of y1, given that Z is 1 and D is 1. And then I have just put in what the values of those probabilities are in this example. So we've got 50% mix of these Y0 outcomes and a 50% mix of these Y1 outcomes. All right, now let's take this expression apart. So we've got a mixture of two kinds of outcomes. Y0 outcomes are untreated potential outcomes. Y1 outcomes are treated potential outcomes. So you see here that we've got this dilution in the sense that the mean of y when z is 1 is actually a mixture of y1. Now that's what we like. That's actually the potential outcome when you get the treatment. But we've also mixed in some y0 there. And it's not just that we've mixed together y1 and y0. We also have to take a closer look at who we're observing y1s for and who we're observing y0s for. So the expectation of y0 when z is 1 and d is 0, what is that? Well, that is the average potential outcome when you're not treated for the sort of family who, when you offer them the voucher, so you give them the opportunity to move to another neighborhood, they don't take it. So this is an average of the untreated potential outcomes for families who, when you offer them the chance to move to opportunity, don't. On the other hand, the expected value of y1, given that z is 1 and d is 1, well, what is that? That is the average treated potential outcome among families who, when they are offered the chance to move to opportunity, z equals 1, they take it, d equals 1. So we're kind of averaging, we're not just averaging y0s together with y1s, which creates this dilution effect. We're also averaging for different kinds of people. So we're looking at y0s for the sort of people who, in some sense, they're really not that eager to move. And we're looking at y1s for the sort of people who, well, in some sense, maybe they seem more eager to move. Certainly, when you make them the offer, they actually take it. We can use a very similar analysis now to decompose the mean of y when z is 0. Again, it's going to be a mixture of y0 and y1 for different types of families. Here, it's no longer a 50-50 mixture because we know that p0 was 0.2. In other words, 20% of the families who were not offered the voucher nevertheless moved to a new neighborhood. Now, here, we are again getting a mixture of y0 and y1. It's no longer 50-50, it's 80-20. But again, we're getting this mixture for very different types of families. So let's take a look at the expected value of y0, given that z is 0 and d is 0. What sorts of families are these? Well, these are the families who, when you don't offer them the voucher, they don't move. So we're computing the average of y0 for a particular type of family. Now let's take a peek at the expected value of y1, given that z is 0 and d is 1. Here we're computing the expected value of y1, that's the treated potential outcome, for the kind of families who, when you don't offer them the voucher, they move anyway. So those are really eager families. They're the ones who they really want to move. So this mean of y, given that z is 0, actually it's got some treated potential outcomes in there, y1, and it's got treated potential outcomes for these families who are really eager to move. So we might actually expect that if they're eager to move, that's because they think moving is really good, or at least good for them. So maybe their y1s are unusually large. The point I'm trying to make on this slide is that while the intent to treat is a perfectly valid causal effect, it is the average treatment effect of offering a voucher, trying to understand the mechanisms beneath the surface, so trying to use the ITT to understand the effect of moving to opportunity as opposed to the effect of a housing voucher, is much harder. It's much harder because there's this conflation between treated and untreated that's baked into each of the two averages. And that just makes it a lot harder to understand what's going on with the treatment itself as opposed to what's going on with the treatment offer, Z. To go further, we're going to need to introduce a little bit of notation and terminology. So on the previous slide, I was referring to different types of families, and I referred to them based on the way that they behave when they see a certain treatment offer. So if you give them a voucher, what do they do? If you don't give them a voucher, what do they do? What we're going to do now is we're going to catalog all possible treatment take-up decision rules. What I mean by that is as we saw on our slide with the walled estimand, it's a ratio of the ITT, which is the causal effect of Z on Y, to the causal effect of Z on D. So the denominator is the causal effect of offering a voucher on whether you really move. What we now want to do is we want to understand that part of the equation. We want to understand the causal effect of the instrument on the treatment. And to do that, we've basically got to consider all the possible causal effects that you could obtain here. So one way to think about this table of different types of families is in terms of decision rules. Another way that's perfectly equivalent is to think about it in terms of different kinds of causal effects of Z on D. So let's go through these one by one and talk about what they mean. First of all, you could have a decision rule that says, no matter what you give me, whether you give me a voucher or not, I am not going to move. What kind of family is that? Well, we'll give them a name. We'll call them never takers. And I'm going to use the notation T equals N. T stands for type. So I'm thinking of 4 types of families. And the first type is never taker, so I'll denote that type by N. So if we want to think about their treatment as a function of their instrument, for these never takers, that function is just 0. D of Z is 0 because no matter what Z you give them, they're not going to take. So for these kinds of families, there is no causal effect of the offer on treatment. There is no causal effect of offering a housing voucher to moving to opportunity. All right, now there is a second type of family for whom there is also no causal effect. This type of family is going to be called always taker. So these always taker families, which I will denote by T equals A, so type equals A for always, they have a treatment take-up rule, D of Z equals 1. So regardless of whether you offer them the voucher or not, they are still going to move. They move with a voucher, they move without a voucher. So this kind of family also has no causal effect of the treatment offer on treatment take-up. Never takers are never going to take. Always takers are always going to take. And the thing that they're taking, or not taking, as the case may be, is the treatment. Finally, we've got 2 types of families that do respond to the treatment offer, the housing voucher. The first type we will call compliers. T equals C, type equals complier. These are the families who do what you tell them, in some sense. If you tell them, here's a voucher to move to opportunity, they move. If you tell them, sorry, no voucher for you, they don't. So for these families, D of Z is equal to Z. They have a causal effect. They are affected by whether we offer them the voucher or not. In fact, the causal effect of Z on D for these families is 1. Without the voucher, they don't move. With the voucher, they move. And since D is binary, we're looking at 1 minus 0 is 1. Now, there's one more possible type of family. You might ask, why are there 4 of these? Well, that's because there are 2 values for the instrument. There are 2 values for the treatment. And so you can do the combinatorics. There are 4 possible decision rules. So the final one, the one we haven't looked at yet, is defier. I'll write T equals D for type equals defier. What kind of family is this? Well, this is the kind of family that somehow has it in for you. You know, they think, wow, these researchers come and offering us vouchers. I don't like them. I just want to mess with their experiment. So what these families do is if you offer them a voucher, they say, a voucher, huh? Well, just because you made my life a little bit easier in terms of making it easier for me to move, I'm not going to move. Whereas if you don't offer them a voucher, they say, no voucher, well, I'll show you. I'm going to move anyway. So the reason we call these families defiers is because in some sense they're doing the opposite of what you would like them to do. You give them the voucher, they don't move. You don't give them the voucher, they do move. So these families are just exactly the opposite of the complier families, and their treatment take-up rule, D of Z, is 1 minus Z, because they do the opposite of what the offer says. So again, these families have a treatment effect of Z on D. You can shift their behavior by shifting their offer, but you just shift it in the opposite direction of what you wanted. So for these families, the treatment effect of Z on D is actually minus 1. These are all the possibilities, and we have listed them. So now we're actually ready to make use of these different decision rules to try to understand what IV means in the case where treatment effects are heterogeneous. And the key idea here is going to be these different families behave in different ways, and it's entirely possible that their treatment effects might be related to the way that they behave. It's entirely possible that the treatment effects for never takers might differ from always takers, that might differ from compliers, and might differ from defiers. And in some sense, that is the problem that we're going to have to solve. So as usual, the way we solve a problem is we assume it away. That's not quite true, but we're going to make a number of assumptions here, and these assumptions will allow us to say something meaningful in spite of the additional complexity that we've added on. All right, so let's add our first assumption. The first assumption here is going to be called unconfounded type. So what this says is for all of those 4 compliance types from the previous slide, so all the 4 types of families that are possible, always, complier, never, and defier, the share of families of a certain type is the same among those who were not offered treatment as among those who were offered treatment. So we're saying among the folks who did not get a voucher, the share of always, complier, never, and defier is the same as among the families who were offered a voucher. If we randomly assigned the treatment, if we randomly assigned the treatment offer Z, then this assumption of unconfounded type is going to hold automatically. And you might worry, well, hang on, what if Z could somehow shift what type you are? But if you go back to the previous slide, you'll see that the whole way that we define these types is in terms of what you do when you get a different Z. So kind of the way we've defined things, it's not possible that Z can shift your type. Your type is exactly a complete description of all the actions you're going to take based on what Z you get. So the way to think about this is, in certain sense, these types are like pre-existing heterogeneity. They're things that make people different from each other, namely how they respond to the offer, that are just kind of out there. They exist before we come in and do our experiment. When we randomly assign the treatment Z, assuming that's what we do, then that treatment is going to be independent of any forms of pre-existing heterogeneity, and that's exactly what these compliance types are. So in a genuine randomized controlled trial, assumption 1 holds for free. If you didn't really randomize the Z, and if Z comes from a natural experiment, then this becomes a substantive assumption. Here's our next assumption. This one is that there are no defiers. So if you want to think about it, what the no defiers condition says is that there are no families who get shifted the wrong way by the instrument. So what do I mean by that? I mean, there are some families who don't get shifted at all. So the always takers are always going to take. The never takers are never going to take. Then there are some families who do get shifted. But what we're saying here is, look, the compliers get shifted from not taking the treatment to taking it. The defiers do the reverse. We're going to assume that actually only one of those directions is possible. So we're ruling out the defiers. We're saying that the only possible causal effect of the instrument on the take-up is to go one way. And what I should say is this assumption does not require that our instrument makes something more likely. We could have an instrument that works the other way. So we could have, instead of a housing voucher that makes it more likely that people will move, we could envision some kind of intervention that makes them less likely to move. That's fine. What we're just saying here is whatever your instrument does, however it can shift people, positively or negatively, it only goes one way. It only goes one way for everybody. So we're ruling out the group of people who move in the opposite direction of what your instrument would otherwise encourage or discourage. That's our second assumption, and it's a substantive assumption. The question of whether there are defiers probably has something deep to do with human psychology. It's not really clear in some settings whether this is a good assumption or a bad assumption. And indeed, there's been a lot of work in recent years that centers around asking whether, and if so how, we could try to relax this assumption. But for today, we're going to be starting with this assumption to see where it takes us. If you want to call this assumption by a different name, you could also think about calling it monotonicity, because what it says is the causal effect of Z on D always goes one way. So there are no people for whom it goes the opposite way of the way it goes for the compliers. Finally, we're going to have two more assumptions. Assumption number 3 is a mean exclusion restriction. So what this assumption says is, For every single compliance type, the average potential outcome, given that you are given your instrument value and your type, does not, in fact, depend on your instrument value. So what does this mean? This means that the instrument itself does not have any effect on the potential outcomes. So this means that the instrument does not directly cause Y. The instrument only affects Y through its effect on D. So we're saying that the mean of Y is 0. It can depend on what type of family you are. It can depend on whether you're an always taker, complier, never, or defier. But it doesn't depend on what instrument you were randomly offered. The same, of course, has to hold for Y1. And you might say, well, doesn't this hold automatically by randomization? And the answer is actually no. You could envision some kinds of instruments, you could envision some kinds of treatment offers that actually do have a direct effect on the outcome separate from their effect on the treatment. In the moving to opportunity example, it's difficult to see why merely offering a voucher would affect people's long-term wage if they did not, in fact, move to opportunity. But there are other situations where, the offer of treatment could have some kind of psychological effect that's actually really meaningful. So imagine that I randomly offered some people a place at Oxford, and they decided not to come, but the fact that that was a possibility meant that they suddenly thought, wow, I can achieve much more in my life perhaps than I thought I could. Like I could have gone to Oxford. Maybe I'm going to think about myself more as like a successful person, and I'm going to go on to work harder. That's possible. I don't know if that's what would happen, but you can definitely think of scenarios where the mere offer of the treatment could have an effect. Finally, we have assumption 4, and this assumption is just that there are some compliers. So there are at least some families who are going to react to the treatment offer. So we've ruled out the defiers, so they're gone, and that means that the only group of families for whom there is any causal effect of Z on D is the compliers. So what we're saying in assumption 4 is there is some causal effect of Z on D. Let me repeat that. Because we've ruled out defiers, we've ruled out one group of families for whom Z does cause D. Remember that the always takers are always going to take. You can't shift them by shifting their Z. The never takers are never going to take. You can't shift them by shifting their Z. The folks you can shift are the compliers and the defiers, but we just ruled out defiers. We said, yep, we're assuming there aren't any. So that means that the only way there could be a causal effect of Z on D is if there are at least some compliers in the population. It turns out that under these assumptions, we can derive some lemmas. If you want to see the proof of these lemmas, you can look in my lecture notes. I just want to make a quick comment, by the way, because a comment I've seen in previous years is, wow, the way that you cover late, it's so complicated. I've seen a much shorter proof in mostly harmless econometrics. That's right. The way I cover it is much more complicated, and there's a reason for this. The reason is precisely that these lemmas on this slide are going to be very useful for thinking more deeply about these late assumptions, and we're going to see why later in this lecture. So I'm kind of going through late in a way that takes everything apart and puts it back together again, and really shows you everything that's inside, rather than just giving you like the slickest and fastest proof. So that's for a reason. And so if you look at this slide, you think, what's all this complexity? I promise there's a reason for it that's coming shortly. So let's take a look at this first lemma. This lemma tells us how we can look at the share of people who take or do not take the treatment, given the value of their instrument, and we can use that to learn something about the share of different types of families that are in the population. So let's start with some easy ones. If you are offered the treatment, Z is 1, but you don't take it, D is 0, then what do we know about you? Well, we have ruled out defiers. There are no defiers. So if you think about it, given that there are no people who are going to do the opposite of what you tell them, then the only people who don't take the treatment when offered must be never takers. Similarly, the share of people who take the treatment when they are not offered, so the probability that D is 1, given that Z is 0, well, that's just got to equal the share of always takers. Why is that? Well, there are no defiers, so the only people who are going to take when they're not offered are always takers. You can use similar reasoning to see why among the people who take when they are offered, we're going to have some compliers and some always takers. So the probability that D is 1 given Z is 1 is the sum of the share of always takers plus compliers. And analogously, the probability that D is 0 when Z is 0 is equal to the share of compliers plus the share of never takers. The reason that this lemma goes through is because of this unconfounded type assumption. So the key point here is that the instrument itself, the randomly assigned treatment offer, say, doesn't have any predictive power for what type of family you are. It's not as though we were more likely to give the vouchers to always taker families because we randomly assigned them. So that's the first lemma. The second lemma relies not just upon assumptions 1 and 2. Remember that 1 and 2 were unconfounded type and no defiers. The second lemma relies upon assumptions 1, 2, and 3, so it adds the mean exclusion restriction. I'm not going to read out all of these equations, but I would like to draw your attention to the two in the middle. So these two tell you that we can learn the average potential outcome of never takers when they are untreated. So we can learn the expected value of y0 among never takers. And the way we can do that is we can look at the average value of y when D is 0 and Z is 1. How come? Well, knowing that someone has D equal to 0, they did not move to opportunity, but they were offered a voucher, Z is 1, immediately shows us that that person must be a never taker. And because we have assumed that there is no causal effect of Z on the outcome, then we are learning the average y0 among never takers. A similar idea shows us that if you look at the folks who did move to opportunity even though you didn't offer them a voucher, so D is 1 when Z is 0, well, who are they? They've got to be always takers. And under this mean exclusion restriction, it tells us that Z doesn't affect the potential outcomes. We can use the average of y for these people, the D is 1, Z is 0 people, to learn the average of y1 for the always takers. As above in the first lemma, the situation is a little more complicated when we're looking at the folks who were offered and did take the voucher, D is 1 and Z is 1, and those who were not offered and didn't take the voucher, D is 0, Z is 0. But the basic idea is the same. We think of what possible types of people these are, and, we'll use some iterated expectations. It brings us to this expression. All right, here is the big theorem. So it turns out that under assumptions 1 to 4, that walled estimand that we started off looking at the beginning of the lecture actually does tell us something meaningful. It gives us the average treatment effect for compliers. And if you think about it for a moment, this actually makes a lot of sense. So for the compliers, remember the compliers are the families who kind of do what you want them to do. When you don't give them the voucher, they don't move to opportunity. When you do, they do move to opportunity. For these particular kinds of families, our experiment is really like a standard randomized controlled trial with perfect compliance. So for this particular subpopulation of families, for this particular subset of all the families out there, it's really just as though we could force them to take the treatment or not, because they're the sort of families who just do what the treatment offer says. So this kind of makes intuitive sense, and the mathematics also shows that it's true. So what happens here? We talked about the moving to opportunity example. In this example, the ITT, which is the numerator of the walled, is the average treatment effect of offering a housing voucher. But the walled is the local average treatment effect. This is defined as the average treatment effect of moving to opportunities for the sort of family who can be induced to move by the voucher that our experiment provides. Now, I do have a derivation here, and I am putting it up on the video, but I don't think that going through this live is necessarily the best way for you to learn it. So I do encourage you to look through the details of this explanation. You may find that what's written on the slide is enough. You could take out a piece of paper and give it a try. You may find that you'd like to look at my treatment effects lecture notes linked from the earlier slides in this lecture. But the derivation is sort of split into two pieces. It doesn't use anything very complicated. It just sort of plugs in those two lemmas. And it has two pieces. finally giving us the result that we want. Basically, we learned that the share of compliers is equal to the denominator of the walled estimand. So again, I am not going to go through these in detail now. It's in the notes. You can use a piece of paper and verify it. So let's move on to talking about what this result actually means. Better late than nothing? Well, if treatment effects are heterogeneous, IV identifies something, and that something is called late, the local average treatment effect. It is the average treatment effect for compliers. But what exactly is a complier? Well, the tricky thing is that the definition of complier actually depends on what instrument we're talking about. It's not like there are people running around with hats on their head that say, I'm a complier, and no matter what experiment they're in, they always comply. It varies with what the experiment's about. It varies with what the inducement to take the treatment is. So let's think about moving to opportunity. My guess is that if you offered people a $1 million voucher to move to opportunity, most of us would be willing to move. So most people would probably be compliers in a world where the voucher was $1 million. On the other hand, if it was $100, maybe there'd be relatively few compliers. Think about it. If the voucher makes it really, really, really attractive, really, really easy to move, more people are likely to respond to the voucher by moving. On the other hand, if the voucher barely defrays the costs of even taking a day off work to look for a new house, very few people might be induced by that voucher to move. So what we've got here is an average treatment effect. It is actually an ATE. It's for some particular group of people, the compliers, but we don't actually know who they are. We can't point to someone in the sample and say, hey, that's a complier. So this is what makes things a bit tricky. My view is that late is not always an interesting parameter. It may be, but it may not be. So imagine an instrument that can only shift a tiny, tiny group of people from being untreated to being treated. And imagine that the sort of people who respond to that particular instrument are highly unusual in some way. Well, how excited would you be to know that you've learned a genuine causal effect for a tiny sliver of the population who are in no way representative of anybody else? You might not be that excited about it. On the other hand, if most people are compliers, or if the particular kind of inducement to take the treatment is in some way directly relevant to some policy questions we have, then the late might be very interesting. To look more deeply at this, however, we would need to build up a set of tools that we don't have time for in this lecture. There is actually quite a lot of interest in going beyond late and asking, is it possible to say anything more than just, I found a causal effect for some people? One fruitful approach to this is called marginal treatment effects. And if you'd like to learn more about them, you can take a look at the lecture notes, and you can also take a look at these two sets of slides that I've linked here. I should say that better late than nothing, well, I've kind of pitched that as a slightly negative outcome. Not everyone takes that view. So there is an article by Imbens, 2010, that argues, well, late is maybe the best we can do, and late can actually be quite interesting. I take a bit of a more mixed view on that point. But one thing that I would like to stress is that no one ever sat down and said, oh, wow, I would really love to know the local average treatment effect. I would really love to know the average treatment effect for the sort of family who can be induced to move to opportunity by a housing voucher in the amount of, $100. No one thought that. No one ever tried to write a paper to learn that particular effect directly. What happened instead is people said, IV seems great, but what if treatment effects are heterogeneous? Is IV actually still giving us a meaningful causal effect? And the answer is, in general, no. So what people did was they tried to think really hard and come up with a set of assumptions so they could kind of rescue IV. So they could say, well, if these assumptions hold, then IV is still giving us something meaningful. It's still giving us a causal effect. It's still giving us a difference between Y1 and Y0, averaged over a large number of people for a recognizable subset of the population. It's just that that treatment effect only tells us about those compliers. It doesn't tell us about everybody. So in some sense, the way that we teach late makes it seem like it was our end goal, whereas in fact, it's kind of like a consolation prize. It's kind of like what we ended up with when we wanted to relax another assumption, the assumption of homogeneous treatment effects, and we discovered it wasn't that easy to do. So we made some new assumptions, and then we said, well, Okay, here's a thing. It's causal. Is it interesting? Sometimes, maybe. And if you want to learn more, again, marginal treatment effects are a fruitful direction. So we can't learn who the compliers are, but in fact, we can learn the average characteristics of the compliers. So what do I mean? Well, let me construct a binary variable here just to give you an example. I'll let f equal 1 if female, 0 otherwise. Then by Bayes' theorem, the probability of female given complier is equal to the probability of complier given female multiplied by the probability female divided by the probability complier. Now, we know from our late derivation earlier in these slides that the probability of being a complier is the same thing as the causal effect of z on d. So in the denominator here, we have the expected value of d, given that z is 1, minus the expected value of d, given that z is 0. And indeed, if z was randomly assigned, that is the share of compliers. That is the causal effect of z on d, because under the assumption that there are no defiers, the only people for whom there is any causal effect of z on d at all are the compliers. So in the numerator, we've still got the same expression as before, probability of complier given female times probability female. Okay, now if the treatment offer is independent of female, which it would be in a randomized controlled trial, again, in an observational study where we hadn't actually randomly assigned the instrument, this would rely on some kind of as good as random assumption, some kind of natural experiment argument. But if z is independent of f, then a really similar argument to that we've already done for the wall denominator above would tell us that the probability of complier given female is actually equal to the difference of means, d given offered treatment and female, minus d given not offered treatment and female. It's a very, very similar argument. If you put these two together, what do you end up with? Well, you end up with the probability female given complier equals the probability female multiplied by something. So we know the probability female, we're assuming that we know this because we can observe that characteristic in the data set. And now what we have is a way to use other things we can observe, dz combined with f, to figure out the share of female among the compliers. So we can't point to somebody and say, hey, that person's a complier, but we could say, well, what proportion of the compliers are female, for example? Now, I started off this lecture by talking about always takers, never takers, defiers, and compliers. Then we assumed away the existence of defiers. But in fact, in many kinds of randomized experiments with noncompliance, and also in some observational data settings, you can't actually get all four of those types. So there are some situations where if you don't get offered the treatment, you just can't take it. An example might be if the treatment offer is a job training program, then it might just be that unless you've got the piece of paper saying that you're allowed to come into this training program, there's no way to get that treatment. So there are many experiments where there's no access to the treatment outside of the experiment. And if that's the case, then there can't be any always takers. There can't be anyone who gets the treatment despite not having been offered the treatment. So in that setting, z equals 0 would imply that d equals 0. And that would mean there are no always takers. It would also mean there are no defiers. So in an experiment with this feature, there are no always takers, and it's not an assumption that there are no defiers. It's just a consequence of the way that the world works. So in that scenario, we can still use our walled estimand, but the expected value of d, given that z is 0, is just going to be 0, since nobody can get the treatment if they're not offered the treatment. And with a bit of extra work, what we can show is that in this case, we still learn the late, we still learn the average treatment effect for compliers, but actually, it turns out that this is synonymous, in this particular case, with the average treatment effect for the treated. In other words, with one-sided noncompliance, where you can't get the treatment unless you're offered the treatment, the late equals the treatment on the treated effect. And that's actually a lot more interesting, because what the treatment on the treated effect tells us is the average benefit of some program for the people who'd actually take it. The reason that's interesting is because in real life, if you're thinking of rolling out some kind of social program, you probably can't force people to take that program. So something like the average treatment effect may not be that interesting. The average treatment effect is the average effect of essentially forcibly treating somebody chosen at random from the population. Well, you can't force people. Then you might ask, what's the average treatment effect for the folks who really would take up this treatment? And that's exactly what the TOT tells us. Another way to look at this is if you were considering getting rid of some program, well, the TOT tells you how much benefit per person you're going to lose. So the TOT tells you the benefits of the program that currently exists for the program participants. So this benefit would be lost if you discontinued the program. So in this special case, the late, which is not always very interesting, turns out to be equivalent to the TOT, which is arguably very interesting. Of course, you could have the opposite. So in the UK, the Butler Act increased the minimum UK school leaving age from 14 to 15 in 1947. If you want to read some more about this, you can take a look at this well-known paper by Oreopoulos from 2005. So in this particular setting, the law says that if you are born after a certain year, you, and that will be Z is 1, you must be treated. You must stay in school until the age of 15. So this is another example of one-sided noncompliance, but it's basically the opposite of the one from above. So in this case, there are no never takers. There could be always takers. That would be people who, even if they were born before the cutoff, would still stay in school until they're 15. But there will be no never takers because, it's the law, and presumably the law is being enforced. So because there are no never takers, anyone with D equal to 0 is a complier. So above, with the one-sided noncompliance that we looked at to start with, anyone with D equals 1 was a complier. Now, anyone with D equals 0 must be a complier. So again, we only have 2 of the 4 compliance types here. We have never takers and we have compliers. The other types can't exist. The reason they can't exist is because of the nature of the policy itself. So in this example, Z equals 1 implies D equals 1. So the expected value of D, given that Z is 1, is just 1. That simplifies the denominator of the walled estimand. And in this case, as usual, so there's no contradiction, the walled estimand identifies the local average treatment effect. That's the average treatment effect for compliers. But here, who are the compliers? Well, the compliers in this particular case, it sounds counterintuitive, but if you think about it, it's correct. The compliers are anybody who you see with D equal to, anyone who you see with D equals to 0 is a complier. So what we actually learn in this case is that the late will give us the TUT effect. In other words, the treatment effect on the untreated. Now, this is actually pretty interesting. So if you think about the idea of putting in a mandatory minimum age of graduating from school, leaving school at 15 rather than 14, the whole idea here is to force people to do something that they might not want to do. So it turns out, and in this case what we're learning is we're learning the average causal effect, not for the people who would choose to stay in school, but for the people who would not. So we're learning the treatment effect on the untreated. We're learning the average causal effect of an extra year in school for the sort of person who wouldn't take it unless they were forced. And if you're considering introducing a paternalistic policy like this one that actually has legal enforcement teeth, the TUT is exactly the kind of thing that you'd want to understand. So with one-sided noncompliance, late becomes a lot more interesting. Depending on the nature of the one-sided noncompliance, we're either going to learn the TOT or we're going to learn the TUT. Now, you might be wondering, is it ever possible to learn both at once? That's actually a bit tricky. It turns out that the answer is possibly yes. So I have a paper with some co-authors where we designed an experiment that actually does allow you to learn both the TOT and the TUT. It's a little bit complicated, but if you're interested in that, you can take a look at my website. You'll see I only have one paper about pawn lending, and that's the one that talks about this particular design. All right, so we've now covered late. We've talked about the assumptions that underlie it, and we've also looked at the special cases of one-sided noncompliance. So what's left? Well, I would like to show you something that's not usually covered in an introductory treatment of late, but I think is really interesting and important, because if we're imposing a bunch of assumptions that we maybe didn't have in the textbook instrumental variables model, and we're imposing them because they give us something nice, something that we like, namely a meaningful causal effect, even in the presence of heterogeneous treatment effects, then we really ought to ask ourselves, do these assumptions make sense? Could we ever test them, or could we ever find any evidence that suggests that they're false? So to answer this question, I actually want to go back, and I want to start by reviewing a little bit of the textbook IV model. So remember the textbook IV model, there were two assumptions. Instrument relevance, namely that the covariance between D and Z is not zero. Can we test this? Sure, because D and Z are observed. Of course, we need to be aware of weak instruments. That raises all kinds of issues for inference. It doesn't raise issues for identification, though. So the Wald estimand is going to be perfectly well defined whenever the denominator is not zero. So this particular assumption is testable, and life is relatively easy. So what's the other assumption that we made in the textbook IV model? Well, that was that the covariance between Z and U is zero. That is called instrument exogeneity. But since U is unobserved, we can't directly estimate the covariance between Z and U. So here's a question for you. If you want, maybe pause the video and think about this for a couple of minutes before we look at the next slide. Could we maybe get the residuals from the IV regression? So not the U's, but the U hats. And could we maybe use those to test the instrument exogeneity assumption? Maybe we could somehow look at the covariance between Z and the residuals. So what do you think? Do you think that would work? Well, I hope that by now I've convinced you of the value of simulation. So when you've got a question like this, you're not sure how to get started, I would advise you to write a little simulation study and see what kinds of insights it provides. It may not give you a definitive answer, but it will almost always give you some food for thought that can help you to design further simulations and maybe help you to carry out some analytical calculations. So simulation is a very valuable tool, and sometimes we get lucky and it actually just shows us what the answer has to be, makes it blindingly obvious, and then suddenly our intuition is able to catch up and we can figure out how to do the math. So what are we going to do now? I'm going to do a simulation with a bad instrument. So what makes this instrument bad? Well, it has a direct causal effect on Y that is separate from its effect on D. So I'm going to load some of my favorite packages here. And I guess I should comment that I'm being slightly old-fashioned here when I load this library AER. A more efficient way to do this is actually to just load the package ivreg, which splits out the instrumental variables functionality from AER, and it's a more modern package. So it's not going to make any difference for this example, but probably in your own use of IV models, you want to just load the ivreg package. It works exactly, the command works exactly the same as the one I'm going to use here, though. Okay, so let's set the seed. What are we going to do here? Well, we're going to simulate some correlated random normal draws. We've learned about how to do that in an earlier lecture. I'm going to call them U and V. I've got a Z, which is my instrument. It's going to be binary. So Z gets our binom N, size equals 1, prob is 0.3. That means Z is a coin flip, but it's a biased coin, so the probability of heads is 0.3. And I've got quite a lot of Z's here. So I've got many thousands of Z's that I'm drawing. What else am I going to do? I need to generate the treatment D. So the way that I have generated this particular treatment D so this D is not binary, which is in some sense it's fine. We can still run IV. It's a bit simpler for me in this case not to make it binary. So D is going to be minus 0.5 plus 0.3 times Z plus V. Then I'm going to set the treatment effect. So beta is going to be my causal effect of D on Y, and I'm going to set that to 0. And now I am ready to generate Y. So how will I do it? Well, I will say Y gets 1 plus beta times D minus Z plus U. So look what I've done there. I've actually written it so that Z has a causal effect on Y. It's right in the equation for Y. And in fact, in this example, the way that I set up the beta, D has no causal effect on Y. But I have made D endogenous, in the usual kind of IV way. I made D dependent on U, and the way I did it was that I generated D from V, which was correlated with U. So this is a simple IV example, and I made beta 0, you could make it something else. But the key point here is the instrument is not excluded. The instrument actually has a direct causal effect on y separate from its effect on d. And let's see what happens. So if I run this IV regression of y on d using z as an instrument for d, and I take a look at the results, what do I get? Well, I get a large negative effect of d on y. I estimate effect of minus 3.5 approximately with a pretty tiny standard error. So we would say, wow, look at this huge and massively statistically significant effect of d on y. Clearly we're getting something wrong. This is the wrong answer. We know that beta is 0. There is no causal effect of d on y, but it looks like there's one because there's actually a causal effect of z directly on y. Okay, well, that's really bad. That's a shame. But maybe if this idea of looking at the IV residuals were a good idea, then we could detect that something was wrong. Maybe we could actually just check that, in fact, z is going to be related to the IV residuals. So what are the IV residuals going to be here? Well, we can get them out by using this function residuals and pull them out of the IV results. And I'm going to compute the covariance between z and those residuals. What do we get? Well, that's 0, or at least that's 0 to machine precision. So, in fact, the instrument is uncorrelated with the IV residuals. And maybe now, if you think about it for a moment, you can realize why that must be the case. The answer is that z is uncorrelated with the IV residuals by construction. In other words, the way that we do IV is precisely by asking what coefficient values will make the IV residuals uncorrelated with z, because the moment condition that we're using to learn those coefficients is precisely expectation of z times u is 0. So let's think about it this way. Let's define u to be the structural error. So that's the error term in the causal model for y. Now let's define v to be the IV residual. So we're going to allow for the possibility that u and v are not the same thing. So v will be y minus the IV intercept minus the IV slope multiplied by d. All right, so what do we know here? Well, we know that beta IV, using our standard expression, is just the ratio of the covariance of z with y and the covariance of z with d. So what does that equal? If we plug in the structural model for y, we know that this is going to give us beta plus the covariance of z with u divided by the covariance of z with d. And we're now going to entertain the possibility that z is not exogenous. So we're going to entertain the possibility that z is correlated with this structural error u, which is kind of like the same thing in some sense as saying that z enters the causal equation for y. Okay, so now, what is alpha IV? Well, that's just the mean of y minus the IV slope multiplied by the mean of d. All right, now, so v equals u if and only if z is exogenous. This is kind of the key point. So this is the only way to obtain beta IV equal beta and alpha IV equal to alpha. So let's take a look here, and let's compute the covariance between z and v. Well, using our favorite rules of covariance and just sort of simplifying things, what do we end up with here? Well, we actually end up with 0. So no matter what, no matter whether beta IV is equal to beta and alpha IV is equal to alpha or not, we're always going to get a covariance of z with v that's 0. And the reason for this is that that was how we constructed the IV estimand. We constructed it by saying, look, this needs to be the thing that makes the residuals uncorrelated with z. And that will hold even if z is not correlated with the structural u. So let me say this another way. If we look at the top of the slide and we take a look at the beta IV and the alpha IV, when are they going to coincide with the truth? Well, they're going to coincide with the truth precisely when beta IV is equal to beta. When is that going to be true? That's going to hold exactly when the covariance between z and u is 0. That kills off the second term in the expression for beta IV. Okay, so what I'm saying here is that alpha IV and beta IV being equal to the true causal parameters alpha and beta, that can only happen. That's going to happen precisely when Z is exogenous. But we just did a calculation that shows that regardless of whether Z is exogenous, Z is always going to be uncorrelated with V. So what we have shown is that there's no way to use the IV residuals to try to learn anything about whether Z is actually an exogenous instrument. It's impossible. Now you may say, wait a minute, what about over-identification restrictions? Couldn't we use that to help us? And the answer is yes. So imagine that we had two instruments. I'll call them Z1 and Z2. And imagine that we assumed that those instruments are both relevant, so they're both correlated with D, and they're both exogenous. They're both uncorrelated with U. Well, what could we do? We could run IV, and then each of them should give us exactly the same parameter, beta. All right, so what if we weren't sure if each of those Z's was actually exogenous? Well, what would we get? We could think about running two different IVs. So one IV could use Z1 as the instrument for Y. That's at the top right on the slide. The other could use Z2 as the instrument. I'm sorry, I misspoke a moment ago. Could use Z1 as the instrument for D. The other one could use Z2 as the instrument for D. And each of these will give us beta plus something, and that something depends on whether the instrument is correlated with U, whether the instrument is really exogenous or not. All right, so if we subtract, so if we take beta 1 IV, that's the IV that uses Z1 as the instrument for D, and we subtract from it beta 2 IV, that's the estimator that uses, or should say the estimand that uses Z1 as the instrument for D, then what are we going to get? Well, the betas cancel out because the causal effect is the same regardless of which instrument we use in this simple textbook linear homogeneous coefficients model. It's the same beta no matter which instrument you use, doesn't matter which one you use. The betas cancel out, and we get a difference of two things. A difference of covariance Z1 with U divided by covariance Z1 with D, minus the covariance of Z2 with U divided by the covariance of Z2 with D. All right, so what does this tell us? Well, if that difference is not zero, then it must be the case that at least one of Z1 and Z2 is correlated with U. How come? Well, if both Z1 and Z2 were exogenous, then the covariance between Z1 and U would be 0, and so would the covariance between Z2 and U. So if they were both exogenous instruments, then the whole thing would collapse, and we would end up with the difference of the two IV coefficients being 0. So if it's not 0, then it cannot be the case that they are both exogenous. One or both must be endogenous. I should point out, however, that the converse is not true. It's possible that the difference could be 0 even though they are both endogenous. How could that happen? Well, if Z1 and Z2 had the same pattern of covariance with U and with D, so if those ratios worked out to the same number in each case, admittedly that's a knife-edge condition, but it's possible, then the difference would be 0 in spite of the fact that both of the instruments are, in fact, endogenous. So this idea of comparing the two IVs, it works in the following way. If we find a difference, then we know something must be wrong. If we don't find a difference, that doesn't prove that everything's okay. And that's because, as I just said a moment ago, the condition that both are exogenous instruments definitely makes the difference 0, but the difference could be 0 even if they were not both exogenous instruments. So this logic actually underlies what is called the over-identifying restrictions test. This is not usually the way that it is taught, and this is not the way that it is actually run in practice, but this is the information that it uses. So that test is a test of the null that all the moment conditions you have identify the same parameters. Now, here's the problem, however. We've been talking about late, And we talked about how different instruments could identify different lates. For example, a moving to opportunity voucher of $1 million might define a very different complier group than a moving to opportunity voucher of $100. So in a world where treatment effects can vary for different groups of people, different instruments define different complier populations, and different complier populations might have very different treatment effects. The sort of people who move in response to a $1 million voucher are probably pretty different from the people who move in response to a $100 voucher. So in some sense, once we begin to entertain the notion of different treatment effects for different people, this whole idea of over-identifying restrictions from multiple instruments goes out the window, because every instrument could be identifying its own late. So that brings us to the obvious next question. Are the late assumptions testable? Well, let's remember what they are. First, unconfounded type. Second, no defiers. Third, mean exclusion. And 4, existence of compliers. Right off the bat, we know that at least one of these is testable. So why is that? Well, that's because assumptions 1 through 3 imply that the share of compliers is equal to the causal effect of Z on D. So the difference of means for D when Z is 1 minus when Z is 0. So assumption 4 is just exactly the same thing as instrument relevance in our textbook IV model. Hence, that's testable. We can just see whether there's more take-up among the folks who were offered the moving to opportunity voucher compared to those who weren't. All right, so we can test something, but we already knew that we could test instrument relevance in the textbook model. The trouble is, in the textbook model, we learned we couldn't test instrument exogeneity. So what about these other assumptions, 1, 2, 3? Can we test them in the late model? Maybe it seems like the answer must be no. Well, this is a slide that is not there to insult famous people who are really, really smart and who I respect. It is merely to point out that this is hard, and this was not obvious. So here's a quote from a well-known paper by Angrist and Imbens. They are referring to this mean exclusion restriction. They say part 1 is similar to an exclusion restriction in a regression model. It is not testable and has to be considered on a case-by-case basis. It turns out, however, that this is incorrect. So as Pearl wrote in 1995, exogeneity can be given an empirical test. The test is not guaranteed to detect all violations of exogeneity, but it can, in certain circumstances, screen out very bad would-be instruments. So it turns out that the late assumptions actually can be tested, or rather, they do have testable implications. This has been known for a while, but there really weren't papers in econometrics that tried to exploit this idea until kind of comparatively recently. So something like 20 years after this original Pearl paper. Today, my discussion is going to focus on the first one, which is a little bit simpler to understand than the others, but you can click on these links to see all 3 if you want more details. And I will illustrate this using a simple and relatively famous example. So this comes from Card 1995. You can read the paper by clicking on the link at the bottom of the slide. Using geographic variation in college proximity to estimate the return to schooling. So the idea here is that Y is log wage, D is a binary variable for whether you go to college or not, and Z is a binary variable for whether you live near to college or not. So this data set is actually very easy to obtain. It's available inside of the Wooldridge package in R. So if you haven't installed that, you can do so now. And we have not, I'm realizing that this lecture now comes in a different order from in past years. So I haven't yet actually shown you this estimator package. Estimator basically can be used to run IV and OLS with robust standard errors very, very easily. So I'm using this because I want to replicate the results of this card paper, and that uses robust standard errors. If you don't know what that means, because we haven't talked about it yet, don't worry about it. I'm running IV, I'm running linear model, and I'm going to compute the standard errors in a particular way because I want to match the paper. So here, my outcome variable, Y, is log wage. My Z is whether you live near a 4-year college. And my D is whether you attend college. So that means greater than or equal to 16 years of education. So I have to do a little bit of setup to begin with here using dplyr, but this should all be pretty familiar by this stage because we're having so much fun with dplyr. And by now, we love the tidyverse because it's just so tidy. Let's use Model Summary, which is one of our other favorite packages, to produce a lovely little output table. So here we've got the OLS effect, and here we've got the IV effect. So if you believe that going to college or not is exogenous, then OLS will tell you the causal effect of college on log wage. So remember that D is binary and Y is on the log scale. So that means that we are looking at basically a percentage change here. So 0.23 on the log scale is like saying upwards of a 20% increase in wage from going to college. That's pretty big. It's not implausibly big. We can sort of imagine that a college premium might have been 20% at the point in time when this data set comes from. It's a pretty old data set. But let's have a look at this IV result, 2.27. Remember, this is on the log scale. So this is not 2%. This is not 20%. This is over 200%. So that's really, really, really large. In fact, I would go so far to say that that is implausibly large. If you see an answer like that, alarm bells should be ringing. So the reason I'm showing you that to begin with is, remember on a couple slides back when I was pointing out that even Nobel laureates make mistakes, and Pearl said, look, we can't always test exogeneity, but we can sometimes screen out really bad would-be instruments. Well, I suggest to you that this probably is a really bad would-be instrument because it gives a result that doesn't make any sense. To be fair to Card, in the paper, Card makes it very clear that you shouldn't just run this IV as is and suggests that you need to control for some other things before the IV plausibly becomes maybe a valid instrument. Okay, but for today, we're just thinking about this question, like, is this a valid instrumental variable when we don't have any of those controls? And remember what the instrument is. It's proximity to four-year college. So being near to college, the idea goes, makes it easier for you to attend by lowering the cost. So we can imagine that Z does have a causal effect on D. But what else might be true about people who live near to a four-year institution? For example, what might be true about people who live near to, I don't know, Oxford University? Isn't there a pretty good chance that they might be children of professors at Oxford University? And if they are, isn't it possible that there might be other things about them that are directly causally relevant for their log wage? Seems pretty clear that the answer is yes. So we should probably be pretty suspicious of this instrument, both when we think about the story behind it and when we look at the somewhat preposterous results that it provides. All right. So let me give you a rough idea of how this Huber and Malache approach works. So let's suppose that all the late assumptions hold. So we've met these assumptions earlier in the lecture. And you may recall that earlier on, I defined some notation, I had some lemmas. So it turns out that if we use lemma 1, then we can take the ratio. It just comes straight out of the lemma. I'm just taking the ratio of two things that are in the lemma. We can take the ratio of the probability that D is 0 given that Z is 1 to the ratio to the probability that D is 0 given that Z is 0. So what's going on here? Let me remind you. If you do not move to opportunity, D is 0, when in fact Z is 1, you are given the voucher, then under the assumptions of the late model, that must mean what? It must mean that you're a never taker. So the numerator is the share of never takers. What about the denominator? Well, if you don't move when you're not offered a voucher, then you could be a complier or you could be a never taker. So this particular ratio, which I'm going to call R for ratio, is the share of never takers divided by the sum of the shares of compliers plus never takers. All right, so now let's think about why conditional on D is 0, Z is 0. Well, what's that? That's a mixture of Y0, the untreated potential outcome, for what kind of people? Well, again, if D is 0 when Z is 0, that means you're either a complier or a never taker under our assumption that there were no defiers. Remember, what we're going to do here is we're going to assume that all the late assumptions hold, and then we're going to see what follows from that. All right, so what does this mixture contain? Well, the whole reason I defined R is because R is quite relevant to answering that question. The mixture contains R times 100% never takers and 1 minus R times 100% compliers. Because what is this R? It's actually the share of never takers relative to compliers and never takers. So that's exactly what we want. We've got this mixture of two types. We know that the share of different types is not affected by the instrument. That was our unconfounded type assumption. So we've now got this nice, simple expression that we're going to put together. All right, so let's begin by calculating R in the card example. Then we'll use that to build our nice little mixture of compliers and never takers. So I'll take the card data. I'm now going to compute the share of people who have D0 and Z1, and I'm going to divide that by the, so I've got P01. So what I'm doing is I'm computing the conditional probability that D is 0 when Z is 1, which I can do by taking these sums. Then I'm going to compute the conditional probability that D is 0 when Z is 0, which I can do by taking these other sums. And now my R is the ratio of the two, and I will pull that out. Here it is, so 0.91. What does that tell us? It tells us that among the people with D is 0 and Z is 0, about 91% of them are never takers. All right, so we now know among the people with D is 0 and Z is 0, what share are never takers and what share are compliers. It's mostly never takers in this card example. So what I'm now going to do is I'm going to make a density plot, and we've seen these already in our lecture on the multivariate normal distribution. So what I'm going to do here is I'm going to take the card data, pull out only the observations for which D is 0 and Z is 0, and I'm going to make this density plot of Y. I'm going to add something else, though. This may be a geom you haven't seen before using ggplot. So I'm using geom vline. What's that? Well, it's a vertical line, and it's got an intercept here, and it's going to intercept the x-axis at a particular location. So what location am I choosing? Well, I'm choosing the 1 minus r quantile of y. So I'll say that again. I'm choosing the 1 minus r quantile of y. Remember that r was about 0.91? So I'm choosing the quantile of y that coincides with having 0.09 of the probability below that point. And I'm going to put that in red with a dashed line. Here it is. So let's talk about this picture. This is the density of log wage among people who did not go to college, D is 0, and did not live near to college, Z is 0. As we talked about, this density is a mixture of the untreated potential outcome, Y0. How do we know it's untreated? Well, because these folks didn't get the treatment. It's a mixture of the Y0 for two types of people. Never takers. Those never takers are people who would not go to college regardless of whether they lived near or far. And compliers. Compliers are the people who would go to college if they lived near. But here we're looking at Z as 0. So they don't live near, so they don't go. So again, we've got a mixture of Y0 for never takers and compliers. And this is log wage. Okay, we already know that this particular mixture contains 91% never takers. The trouble is we don't know where they are. So somewhere in that density, hiding in plain sight, are 91% never takers and 9% compliers. We don't know who's who, but what we do know is that the dashed red line is the line such that 9% of the density is below the line, and 91% of the density is above the line. That's important, so I'd like to say it again. The dashed red line is the line such that 91% of the density is above and 9% of the density is below. All right, so we don't know where the never takers are. We just know that there's 91% of them. So they could be anywhere. But in a certain sense, what's the worst case possibility? Well, it's possible that the never takers are all at the top of the distribution. Maybe the never takers all have the highest wages. Well, if so, then that would mean that everybody above the red line was a never taker and everybody below was a complier. Now, I'm not saying that that's actually true. I'm not saying that's where they are. I'm saying that's possible. And the reason why we want to think about this is because that possibility corresponds to the highest average wage for never takers that we could possibly obtain given what we know. We know that in this picture we've got never takers and compliers. We know that 91% of the people are never takers. They could be anywhere. But if I put any of the never takers below that red line, then that's going to pull down their average log wage. So the way to make the never takers have the highest possible average log wage will be to put them all above the red line. So the assumption that they're all above the red line corresponds to asking, what's the highest possible average log wage that the never takers could have that's consistent with everything that we know? Okay, so again, we have a density of Y0 for a mixture containing 91% never takers and 9% compliers. If all the never takers are at the top of the distribution, then they're above the red line. And as I tried to argue a moment ago, this is going to imply that the mean of all observations above the red line gives us an upper bound. It gives us an upper bound for the expected value of Y0 given never taker. That is the highest average wage the never takers could have. And remember, the never takers are untreated. We're looking at this distribution of untreated people. So we now have a bound. If we can just take all the data above the red line and compute the average of that part of the density, we're going to have an upper bound for the expectation of Y0 given that T is equal to N. The average untreated wage, log wage, for never takers. Okay, great. But wait a minute. If you go back quite a few slides, you'll find that lemma 2 actually showed us what value that average should take. So lemma 2 actually showed us that the expected value of Y0 for never takers must be equal to the average value of Y given that D is 0 and Z is 1. So this is actually important enough that I really want to emphasize it. We have these late assumptions. They imply that we know the mean of Y0 given T is equal to N. We know the average log untreated wage for a never taker. It's just an average of Y for D is 0 and Z is 1. That's because under our assumptions, crucially no defiers, anybody who is untreated but has the instrument turned on must be a never taker. So we already know that average. And now you must be wondering, well, why do I want to construct an upper bound for a thing that I already know? Well, the answer is, think back to that over-identifying restrictions test. Remember how we thought about having two possible instruments? Why would I bother having a second instrument if I already have one? Well, the answer was that second instrument could provide over-identifying information. Under the assumption that both instruments were giving us the same, should have been giving us the same causal effect, seeing a difference would show us that something is wrong. Well, here we're doing something with a similar flavor. We're saying, look, our assumptions imply that the expected value of Y0 given T is N is just known. But our assumptions also imply this other thing. They imply this bound. They imply this bound, and crucially, that bound is a piece of, you might call it, over-identifying information. It's something that we didn't need when we computed the late. The late does not involve taking the expectation of all the stuff that's above this particular quantile in the log wage density. We don't even form any densities when we're computing the late. So in some sense, this picture it gives us some genuinely new information. Admittedly, that information is only a bound, but it's genuinely new information that flows from our assumptions, information that is implied by those four assumptions that we made, but information we have not yet used. So, if that new information that the picture gives us contradicts the result of lemma 2, then what do we know? We know that something must be wrong with our assumptions, because if our assumptions imply a contradiction, well, they can't be true. So what we're going to do is we're going to take a look at two numbers. One of them is the mean of all the observations above the red line. That's an upper bound for the expected value of y0 among never takers. Then we're going to directly compute the average value of y when d is 0 and z is 1. According to our assumptions, that should be equal to the expected value of y0 among never takers. So if that average is above the upper bound, clearly something must be wrong. All right, now this is a little bit more complicated, so I'll walk you through the logic. So at the top of this slide, I am showing you the bound. So the bound says that the expected value of y0 given never taker must be less than or equal to the average value of y given that d is 0, z is 0, and y is above that red line. So I'm going to compute the average value above that red line. How can I do that? Well, first I'm going to take the card data. I'm going to filter out the observations. I'm going to filter such that I only keep the observations where d is 0 and z is 0. Then I'm going to compute. I've got the 9th percentile here. That's this quantile of y, the 1 minus r quantile. And now I'm going to compute the average of y for the observations of y that are greater than or equal to that 9th percentile. And I'm going to pull it out. So again, if you find that code confusing, you might want to take a moment to think about it. But all that I've done here is I've computed the average using the density from the previous slide when I cut out everything that's below the red dashed line. So if I take that density, I cut out the bottom, and I take the average of what remains, I'm going to get around 6.15. But as I mentioned before, our assumptions also imply that we can directly compute the expected value of y0 given that t is n. How do we do that? Well, we just look at the average value of y when d is 0 and z is 1. I'm going to compute that, and I get 6.25. That seems to present a problem because this is actually above our upper bound. So something must be wrong. Now, you may look at this and say, well, that difference may not be statistically significant. If so, then congratulations for thinking about something that's very relevant and important. I'm not going to go through doing inference here, but it turns out that actually, if memory serves, at least, that is indeed statistically significant. So this difference is large enough to be meaningful. And the point that I'm trying to make here is, well, in fact, you can sometimes test the late assumptions. So you will not always be able to find violations. You can construct scenarios where the assumptions are false, the late assumptions do not hold, but this approach that I'm using here does not, in fact, reveal a discrepancy. However, sometimes with a sufficiently bad instrument, you can indeed find a discrepancy. Now, I have not walked you through all of the implications of the late model. There are some other inequalities that you could check too. If you want to learn more about those, you can take a look at my lecture notes. You can also take a look at the paper. So I've only shown you the one bound that fails. But the key point to take away from this is, in fact, the late assumptions can, in some cases, be tested and can be shown to be violated. The approach that we use is a little bit like the over-identifying restrictions test in some sense. And the reason why we can do this is precisely because the late assumptions actually impose more structure on the problem than the original textbook IV assumptions. So whereas the original textbook IV assumptions do not allow us to test instrument exogeneity, the late assumptions sometimes can.